Welcome back to Math 256. This is Scott. Let's get started. We are now in the final phase of our course, the last chapter that we're going to study, and that's chapter 6. And in this chapter, you are going to be introduced to a process which at first might look a little strange, but soon I think you'll agree is extremely useful and fun. So what we're going to be talking about here in chapter 6 is Laplace transforms. So Laplace transforms. Let's figure out what those are all about. This is 6.1, the Laplace transform. All right, the Laplace transform is an operation that allows us to basically convert a differential equation into an algebraic equation. So here's the basic idea. The Laplace transform turns a function of t into an algebraic expression in S. And then the notation that we use here, what we write is we write the Laplace transform, and you do that with a little script L, just a fancy little L. And then by universal custom, it is written now with braces. So this is like a set brace, where it looks like it. So a squiggly brace. And then you have your function f of t. And this produces some other expression, f, which is an expression in S. So this represents the Laplace transform of f, and this does not, I repeat, does not represent the antiderivative. So this is the Laplace transform, not the antiderivative. Okay, so then the purpose of all this, so what's the point of all this? The point of all this is to turn a differential equation into an algebra equation. So the reason for doing this is that the Laplace transform turns differentiation into an algebraic operation. And what that means is, so then what that means is that we'll use this later. First, we have to figure out what this even is, how to find it, things like that. But when we've mastered the basics of Laplace transforms, here's how we'll use them. How we'll use this. So we'll start with an ordinary differential equation, in particular, an initial value problem. we'll use the Laplace transform to turn that into an algebraic equation. And then we'll do algebra, so then solve. And that gives you the solution in S, but S is a new variable that we're just making up. So then what we do is the inverse Laplace transform, which will take us back to the solution in T. Okay, well, that's what we're going to be doing once we've figured out how to do it. Now, let's start figuring out how to do it. So let's define our terms here. The definition. So if f is a function that is, so I'll just say it now, we won't bother writing it, we'll deal with this later. But if it's a function of less than x, or of exponential order, so f is a function, and it's defined for all t greater than or equal to 0. Then the Laplace transform of f is equal to the integral from 0 to infinity. So let's stop right here for a second. So the integral part of this hopefully will make a lot of sense, because after all, if we're trying to make something that will convert differentiation into something a little bit nicer, it shouldn't be too surprising that there's somehow an integral involved in it. So then, if this is the if this is the integral from 0 to infinity, and just a spoiler alert, it's going to be the integral with respect to t, then here what we'll put is e to negative st, and then f of t dt. So if we look at this, it is integrating with respect to t, and it is a definite integral. So it's a definite integral, although it is improper. It goes all the way from 0 to infinity. But it is a definite integral in t. So when all of the integration is done, all the t's will be replaced by 0 and infinity, and there won't be any t's left. The only variable left standing will be the s. So that is how this will convert it into an expression in s. So let's set some goals for ourselves. So goal one. We want to make a catalog of the Laplace transforms of all of our greatest hits, all of our most familiar functions. Of the Laplace transforms of familiar functions. And when we say familiar functions, some of these will be more familiar than others, but a lot of new friends will also be coming our way. All right. So let's look at a tool that's going to come in a lot of handy. Our basic goal in doing this is going to be to actually directly integrate the expressions as seldom as we can get away with it, because it is a little bit cumbersome to actually do all the integrations. And if there's any way around it we can find, we'll want to use it. So the tool that we'll use is the tool of linearity. All right, so just as a note, if we think about the definitions of the integrals that we're talking about here, then if I were to take an expression of the form, the integral from 0 to infinity e to the negative st, and in here, instead of just having f of t, I were to have a f of t. So just a constant multiple of f. And then, in fact, while I was at it, I put in another function, g of t, and I gave it a constant multiple, g of t. And I put this in instead of the original integrand. Then I can see that because integrals split up term by term, we can rewrite this as e to the negative st, a, actually better yet, I'll bring the a all the way out to the front. After all, integrals are linear in the sense that a constant multiple of the integrand can be pulled all the way out to the front, plus b, integral 0 to infinity, e to the negative st, g of t, dt. And so therefore, thus, which is the math way of writing therefore when you don't want to write the longer version, what we have is the conclusion that the Laplace transform of a f of t plus b g of t is actually just going to be the Laplace transform of f with an a out front plus the Laplace transform of g with a b out front, or if we write it according to the standard notation here, a capital F of s plus b capital G of s. So what this means is that whenever we are able to break something into a sum of known functions, then we are off to the races. So this will come in handy. But first, let's start as simply as we can. So catalog. Make a catalog of our Laplace transforms. All right, let's start simple. F of t is just going to be the constant function 1. So f of t just equals 1. Functions don't get much simpler than that. Hopefully, this will be a good place to get our feet wet. So, how do we find the Laplace transform? F of s is equal to, and we're just going to go directly for the integral for this because it's so simple and we have no other place to start. And then we're going to hopefully soon be able to stop using the integrals directly and make pieces out of known functions. All right, we have e to the negative st dt, and here, if we think about this, it is an integral with respect to t. So as far as t is concerned, s should just be treated the way you would treat a constant. And so the chain rule would just bring negative 1 over s out to the front. And what we would have is e to the negative st going from 0 to infinity. This is a definite integral, remember. So now, if we think about what the pieces of this will each be, we have a negative 1 over s. We have first off, plug infinity in here. what are you going to get when you plug infinity in for t? Well, it's going to be e to the negative s times infinity. So as long as s is greater than 0, this is just going to go to 0. So as a note here, so e to the negative st goes to 0 as t goes to infinity if s is greater than 0. So the actual values of s here are not really relevant to us. S is a dummy variable that we just made up in our definition of the Laplace transform. It is merely an undetermined or an indeterminate form. It is not actually an input to a function or anything like that. S does not really assume values. S is just an algebraic stand-in. But here, we plug in t equals 0. We'll just get e to the 0. And so what do we have? We have negative 1 over s times negative 1, which is going to just equal 1 over s. Okay, we have accomplished our first Laplace transform. The Laplace transform of the function which is constantly equal to 1 is 1 over s. All right, well, what do you say we up the ante a little bit and we make it not the function that is just constantly equal to 1, but let's make it the function f of t equals t. So pretty much, oh, by the way, once we found the constantly equal to 1, we found every constant function by the linearity. But now let's take our next stab. Let's move up to linear functions. So f of t is just equal to t. All right, well, here we go. We can't really do anything other than just go directly to the integral at this point. We don't have any other tools really available to us, so we will just integrate and see what happens. So we're good. We have the integral from 0 to infinity, e to the negative st times t dt. And so now, if we think about where this is going to go, we're going to need to do some integration by parts in this. So we need to cast the roles of u and dv. And here we have a t as one of our functions, and that typically makes for a pretty good choice for u, because remember, the basic strategy in integration by parts is anytime that you have something that will get simpler when you take its derivative, then that usually makes a good choice for the u. So t is something that gets simpler under differentiation, and in particular, dt or du equals dt. dv then is just going to have to be the rest. It's going to have to be e to the negative st dt, which then means that our v is going to be the antiderivative of this, which is going to be negative 1 over s e to the negative st. And that then means that when we do this integration by parts, remember that the integral of u dv is equal to the u times the v minus the integral of v du. That's how integration by parts all works. And if it's a definite integral, then you plug in values in both parts of this. So what do we have? We have t times negative 1 over s e to the negative st, and this is going to be evaluated at 0 and infinity. And then what else do we have? Minus the integral of v du, which is going to be integral 0 to infinity, negative 1 over s e to the negative st dt. And so now the integral has become simpler than it was to start with, and that is always the goal when you're doing an integration by parts. Bracketing this off so I can continue this down here. All right, and then here, let's say that so if s is greater than 0, sorry, if s is greater than 0, so if s is greater than 0, then t e to the negative st goes to what as t goes to infinity? Well, if we think about this, t versus e to the negative something times t. We're talking about exponential decay versus linear growth. Who wins in the long run? So the winner will be exponential. So exponential growth / decay will always swamp linear growth / decay. So this goes to 0 as t goes to infinity, and this is because exponential beats linear. If you didn't trust this, you could use L'Hopital's rule and show that was true. Okay, so that's an aside, an aside, an aside. All right, back to the main event, which was this valuation. If we plug in infinity here, what are we going to have? We're going to have negative 1 over s times 0, as we just said, minus, and then what are we going to have if we plug in 0? Looks like just going to be another 0. All right, minus an integral from 0 to infinity. So I'm just going to go ahead and bring out the negative 1 over s to make it positive. And now I will we'll set up camp right there. E to the negative st dt. So what's this equal to? Just 0. So we just have this part. So it's 1 over s. And then if we actually take this integral, we've done this before, it's going to be negative 1 over s e to the negative st. We're plugging in 0 to infinity. And by logic that we have already seen here, we have, well, first off, we can pull out the negative 1 over s. It's negative 1 over s squared. And here, if we plug in infinity, then we're going to get a 0. And if we plug in a 0, we're going to get a 1. And so we have 1 over s squared. Okay. Well, that means then the Laplace transform of t is equal to 1 over s squared. Interesting. So if it was just a constant, it was 1 over s. If it was just a t, it was 1 over s squared. What's the pattern here? It appears that the higher the power of t, the higher the exponent on the s in the denominator. And that is in fact true, and it continues. All right, but let's take a victory lap here. What if I wanted to then find the Laplace transform of a combination of all of functions that we have already explored, at least representatives of? So this is where our linearity can come into play. We do not need to set this up as an integral and work from scratch. We have all of the pieces of this already analyzed. We know that the Laplace transform of just a t is 1 over s squared. We know that the Laplace transform is linear, and so that 3 just carries through to the front of that. We know that the Laplace transform of just the function constantly equal to 1 is 1 over s. And we know that the Laplace transform is linear, so that 2 can just carry through. And so, if we want to simplify this a little bit, we can say 3 over s squared plus 2 over s, and if I want to simplify this even further by finding a common denominator, I can do so. So it would be an extra factor of s for the second term here. So it's going to be 3 plus 2s over s squared would be our final answer there. All right. Well, let's think about how this actually played out. What actually happened as we did this integral, and so that we can perhaps try to glean a pattern if we were to continue the process. When we did this with t rather than just a constant, the difference was that it required an integration by parts. And this integration by parts led to us basically creating a recursive process that eventually ended up being the original expression all over again. But as it went through, it ended up getting extra factors of s in the denominator. And actually, as you produce these, you'll get extra copies of each of the terms. And so the way it will actually work out, so we'll skip to the general pattern here. So the general pattern is, in some ways, expected, and in other ways, surprising. So if n is a non-negative integer, so in other words, an integer that is 0 or higher, then the Laplace transform of t to the power of n is actually just going to be n factorial. So whatever the power is of t is going to be that factorial on the top, and s to the n plus 1 on the bottom. And remember how n factorial works. So 0 factorial equals just 1, 1 factorial equals 1, 2 factorial equals 2, and all factorials higher than that are made by just multiplying the numbers together till you get to n. So n factorial is n times n minus 1, until you get down to just 1. So each number, so you need a kind of a starting definition, and then each new number up is made by just multiplying together the numbers below that. All right, well, let's try this. Try actually using this in a simple way. We'll discuss maybe at a later point why this pattern holds exactly. I gave you a rough idea. If you wanted to, you could go through some of the motions of the actual integration by parts and see what happens. But here, once we have observed that there is a pattern, we are going to just go ahead and use it shamelessly. Okay. So how would I find the Laplace transform of something like 2t to the third? Well, I just would identify that n equals 3, and I would just go ahead and accept the formula for what it is, and I would say I have an extra factor of 2 here, then it's going to be 3 factorial divided by s to the fourth. whatever the power of t is, it's 1 higher than that in the denominator of the Laplace transform. And 3 factorial is 3 times 2 times 1, which is 6. So this is going to equal a total of, looks like 12 over s to the 4th. So that's how that goes. Now, what if what if the power is not a non-negative integer? In particular, what if it is not an integer at all? And we'll just say, what if it's a fraction, for example? So if the exponent is not an integer, we can use a generalized version of factorials called the gamma function. And in particular, the gamma function, which is written with capital gamma, which looks like that. It's like an F, but it doesn't have that extra little bar there. Gamma of x is defined to be the integral from 0 to infinity e to the negative t times t to the x minus 1 dt. So you'll notice this looks actually kind of similar to the definition of a Laplace transform, but this is an integral that is just defined in order to create the gamma function. Now, I say this is some sort of a generalization of factorials. How so, you wonder? Well, if we were to integrate this by parts, so I'm going to just tell you what would have happened if we chose to spend some time doing that. Unfortunately, it's a heavy time commitment, and we're on a tight schedule here, so we can't. But so if we did integrate by parts, integrating this by parts would teach us that that gamma of x plus 1 is equal to x times gamma of x. Also, gamma of 1 happens to equal 1. And then, so thus, together, we would get gamma x plus 1. So if we just start applying this, it would be x times gamma of x. What's gamma of x, though? Well, it has the same relationship to x minus 1 that x plus 1 has to x. So we could actually just repeat this. It iterates in a very similar way. And this will be x minus 1. And then what happens next? Pretty much the same thing over and over again. And so we get x times x minus 1 times x minus 2, dot, 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 till we get down to just 1 times gamma of 1. This is if, or whenever. whenever x is a positive integer. So what that means is that gamma of x plus 1 is equal to x factorial. Alternatively, sometimes it's more useful to word this as gamma of x equals x minus 1 factorial, whichever is more useful for our purposes, is the one that we would make more use of. And then the Laplace transform fits in nicely with our previous pattern. So our previous pattern only applied when x was an integer. The gamma function, however, is defined whenever x is anything basically other than -1. It just, when you happen to plug in an integer, it happens to give you the same thing as the factorial. But anyway, so then the Laplace transform of t to the alpha, where alpha is any power that's not specifically a negative integer. So alpha can be anything. Is equal to, well, in the old days we would have seen a factorial on the top, but the factorial might not be defined here if alpha is not suitable for factorialization, namely it's not a positive integer. So what we can do is on the top have alpha plus 1 inside the gamma function, which is the equivalent of a factorial, and then down here, oops, not t, s to the alpha plus 1. And this is defined even for non-integer values of alpha. Now, it may be defined, but it's not like we just happen to know off the top of our heads frequently what the gamma function is when we plug in things like a half or 3/2 or things like that. So if we actually want to evaluate it, we do need to know some extra information. So to actually evaluate the gamma alpha plus 1 it helps to know certain facts. So one of these facts is what we just said. So gamma alpha plus 1 is the same as gamma alpha times, not gamma alpha, I mean alpha times gamma alpha. And there's an amazing fact that comes to us from multivariable calculus, that the gamma of 1/2 is equal to the square root of pi. Now the origin of this is, so this comes from the amazing fact that the integral from -infinity to infinity of e to the negative x squared dx happens to equal square root of pi. So you can, so this fact comes from this fact. This fact can be proved using some of the techniques from Math 254, for example. As strange as it may look, what does e have to do with the square root of pi? Like seemingly nothing. But it turns out that this is the case, and this is a fact that actually has a lot of significance in statistics, because this function right here is the function that dictates the shape of the normal distribution. That's the classic bell-shaped curve that is famous in statistics. So these are just some interesting facts. We don't have time to get into the proof of all of them. All of them can be proved, and they are not actually as hard as they seem, but they do take us a little bit beyond our brief. So we won't be able to actually get into the nitty-gritty of that at the moment, unfortunately. But what we can do is use it. So using this. So let's just say I wanted to calculate gamma of 3/2. All right. Well, how can I break this into pieces that I can already work with? Well, if I am playing this game here, 3/2, I would want to write that as something plus 1. So it's 1/2 plus 1. So here that means, in other words, alpha is just going to be playing the role of 1/2. So then what's this going to equal? It's going to equal alpha times gamma alpha, 1/2 gamma 1/2, which would be 1/2 square root of pi. All right. Well, what if I gave you something a little more challenging, like 7/2 as our gamma? So 7/2 is the input of gamma. So then what you could do is same process. You just rewrite it as something plus 1. This would be 5/2 plus 1. And so what's that going to equal? So here then our alpha is going to be 5/2. So we would just bring out the 5/2, and that's gamma 5/2. But what's gamma 5/2? Well, that's gamma of, we just repeat the process. Rewrite it as something plus 1. So that means now our alpha is 3/2. And so what we would have is 5/2 times 3/2 times, and now we can actually start to see the pattern, and maybe you can figure out where it's going to go from here. But it's just going to become gamma of 1/2, and so actually 5/2, 3/2. Let's not jump the gun here. So then that's going to be gamma of 3/2, which we'll earn our gammas to start with, and then once you get the hang of it, you can hopefully just extrapolate a pattern. This is gamma 1/2 plus 1, so we're just, so technically we already know gamma of 3/2, but it's kind of nice to go through this just a little bit in the beginning anyway. So 5/2 times 3/2 times 1/2 times gamma of 1/2. So altogether, what do we have? We finally have it down to something we know. So it's going to be 15 on the top, 8 on the bottom, square root of pi. So the gamma function, it is a known fact of nature that it is equal, or that gamma of 1/2 equals root pi. There are other known facts of nature for other important values. the gamma functions, such as 1/3 and things like that. But in this course, basically all the tricky ones we do are going to be based on 1/2. Those of you who want to learn more about the gamma function, obviously this class is merely a beginning, not the be-all end-all in learning about these things. So let's try this as an example. Let's try to find the Laplace transform of t to the 5/2. Okay, well, we think about this. This is t to the alpha. Here, alpha equals 5/2. So what do we have here? We would have, so we have the gamma of alpha plus 1. We would have had a factorial if this had been an integer, but it's not. And down here we have s to the 5/2 plus 1. So what's that? That's gamma of 7/2 over s to the 7/2. And gamma of 7/2 we have already found to be equal to 15/8 root pi divided by s to the 7/2. So that's how that gets done. Now, that's about as far as we can go on just pure power functions or constant functions, things like that. If we want to go into any of our other interesting functions, we're going to have to start thinking about exponential functions, trig functions, and hyperbolic trig functions. So let's bite the bullet. Let's go for it. So next specimen here, f of t equals e to the at. This is as simple a case as we can hope to look at. So let's just get back to the basics, start with the definition of the Laplace transform and work from there. So f of s equals the integral from 0 to infinity e to the negative st e to the at dt. All right, well, I see some stuff in common here, so let's go ahead and factor out the t, so we can combine these two pieces, and that will make e to the t times a minus s dt. And then if we are integrating this, the t is the variable. Everything else is to be considered a constant, so this is going to be 1 over a minus s times e to the t times a minus s, and now let's remember this is a definite integral, 0 to infinity. And now we can think about what it's going to take for this to be defined as t goes to infinity. So if s is greater than a, then e to the t times a minus s will go to 0 as t goes to infinity. In all these cases, these are technicalities that we're just considering so that the integral in question converges. If the integral in question does not converge, then the Laplace transform is not defined. But these conditions are not really as strict, they're not as meaningful as they appear, because remember, s is just a dummy variable. S does not actually take values. S is not an input variable for a function. It is merely an indeterminate, which we're creating algebraic expressions around. Okay, but what's this going to mean then? 1 over a minus s. And by the way, we can appreciate that this was a nice integral. It was very clean, and we hope that none of our integrals are going to be any messier than this going forward. 0 minus 1 I'm going to plug in the two bounds of integration. So what's that going to be? It's going to be negative 1 over a minus s. But what's that? Well, a negative can be brought down into the bottom, distributed in, and that's going to be s minus a. All right, good to know. Now, it turns out that by a very similar process to this, we can actually extend this a little further. And I'm just going to go ahead and make a note of that right now, just because it'll be a useful note, and it'll be more useful to just have it in the bank than it will be to derive it. So note, if the Laplace transform of f of t equals capital F of s, then the Laplace transform of e to the ct times f of t is actually just going to be the same basic function, just where there was an s, there will instead be an s minus c. And this actually, you can see in the exact case that we just did, this would apply to f of t, or f of t being e to the at times the constant function 1. And it turns out this carries through. And the reason why this always works is that it actually does pretty much the same effect on the exponent of the Laplace transform here that we saw above, and so the same sort of pattern would continue in other cases. But this is just a note, so it just gives us a little bit more heft to our catalog. And now let's see if we can make the most hay out of this as we possibly can. So trig functions. Trigonometric functions. And the key here is going to be the key that we always have, which is Euler's formula, or Euler's equation, Euler's identity, however you want to word it. E to the I x is the same as cosine x plus I sine x. Okay, well then, let's think about the Laplace transform of e to the it. Actually, ikt, I'll put k in there. So, what's that going to be? That's going to be the same as the Laplace transform. Actually, by what we've just found. This is going to equal 1 over, and down here we're just going to have s minus ik. That's where I want to go with this. Okay, but then what? Well, as we've seen before, our typical approach on things like this is going to be to multiply by a conjugate, and then we can start thinking about real and imaginary parts. So s plus ik, s plus ik. Where does that leave us? That leaves us s plus ik for the top. And at the bottom, we're going to have s squared. And then the middle terms cancel, like all difference of squares up calculations. And then at the end, we're going to have an I squared. We're going to have a minus, and so the I squared and the minus will cancel each other. We'll have a k squared. So plus k squared. Now, if we break this up into its two pieces, s squared plus k squared, and then an I in front of the imaginary part, k s squared plus k squared. Then what we will have is something that we can then equate with the cosine and the sine parts. So thus, if we take just the real part, that's going to be giving us the cosine. So the Laplace transform of cosine kt is equal to s over s squared plus k squared. Meanwhile, the Laplace transform of sine of t, the sine of kt, is equal to k over s squared plus k squared. By the way, your book does not use a k here, it uses an a, I think, if I remember right. I like to use a k. Here's the reason why. It helps suggest a mnemonic. So I can, so to help remember which of these is which, I just remember k for cosine, but it switches. So I know this is a little bit of a backwards mnemonic, but k for cosine, but it switches. So the cosine has the s on the top, the sine has the k on the top. Other than that, they have pretty much the same formula. So I just remember k for cosine, but it switches. I know it's a weird mnemonic, but I find it helpful, and nobody has ever told me it wasn't. So we'll go with it. Just as a note, s has to be greater than 0 for this to happen, but we don't worry that much about the restrictions on the s, because like I said, s does not itself actually assume any values, so it's not really as important as it would be if these were really functions of s. Okay, now let's talk about the hyperbolic. The hyperbolic trig functions. So by definition, we have the hyperbolic cosine and the hyperbolic sine, commonly pronounced cosh and sinh. We can define them to equal 1/2 e to the x plus 1/2 e to the negative x. This one is 1/2 e to the x minus 1/2 e to the negative x. There are other ways of relating them to the sine and the cosine, and in fact, you could even refer you to some of the in-class explorations that we've done of these very things on the recorded Zoom meetings. But anyway, then if we want to actually look at these two functions piece by piece, if I wanted to do the Laplace transform of the hyperbolic cosine, kt, oops, I can use the linearity, 1/2 of, and then here what we would have is that e to the x, e to the kt, which is 1 over s minus kt, sorry, s minus k, I should say, and then plus 1/2, and it's 1 over s plus k, so s minus negative k. And so what is this? It's 1/2 of s plus k, s minus k. So if I want to combine these into one expression, which I do, I'll need a common denominator. So I'll multiply this one by s plus k over s plus k. I'll multiply this one by s minus k over s minus k. And what's that going to leave? It's going to leave 1/2. We're going to have s plus k plus, and I'll just go ahead and combine them all. I pulled out a half, s minus k. Down here, s squared minus k squared. And so this equals 1/2, k's cancel, 2s on the top, s squared minus k squared. Now the 2's will cancel, and so that gives us s over s squared minus k squared. Now, okay, so that's the, I'll go ahead and put that in, this, so the Laplace transform of cosh kt equals that. Don't worry, we'll make a grand table summarizing all of our findings. Okay, by the same token, if I want the Laplace transform of sinh kt, things would go very similarly, except where they don't. So in particular, I would just have 1/2, 1/2 1 over s minus k minus 1/2 1 over s plus k. So by very similar reasoning to above, 1/2. So let's think about this. It's going to be, we're going to have s plus k minus s minus k. And then down on the bottom, it's going to still be s minus k, s plus k, so it's going to be s squared minus k squared. So what's that going to be? It's going to be 1/2 2k s squared minus k squared. And so when these cancel, we get the Laplace transform of sinh kt is equal to k over s squared minus k squared. Okay, once again, I like writing these with k's for the same reason I like writing the circular trigonometric functions with k's. It helps to be a little bit of a mnemonic. So cosine goes with k, but it's backwards. So sine, cosine, s, k, but it's backwards. Now, one other mnemonic that I like to use to help keep things straight would be the fact that on the trigonometric functions, the difference is that it's a plus in the denominator. In the hyperbolic ones, it's a minus. So one way you could remember that is T for trig. So it's plus T for trig. Plus looks like a T. T for trig. All right, now so if we want to do a lot of things involving trig and these functions, then it's useful to have some trig identities under our belt. So here are some useful trig identities. And when I say useful, I mean they'll just come in handy for problems that we are about to try. So sine squared x equals. So you may know a couple ways of rewriting this, but here's the way that has proved to be most useful most often in calculus, in your experience. 1/2 minus 1/2 cosine 2x. If you ever had to take the integral of sine squared, then basically the only way to make any headway on that is to use this identity. Sometimes it's called the double angle or the half angle identity. It's pretty much the only game in town if you want to integrate something like sine squared. By a very similar token, cosine squared x equals pretty much the same thing, just with a plus. Okay, well, then how is this going to be useful to us? Well, let's just say I had as an example the task of finding the Laplace transform of cosine squared t. Well, I don't know how to take the Laplace transform of cosine squared directly, and if I tried to turn it into an integral, I might be getting myself in over my head. But wait, if I look up here, it turns out that the cosine squared is actually, by the magic of trigonometry, is actually expressible as a sum of functions that I can get some traction on. So this is going to equal 1/2 the Laplace transform of 1 plus 1/2 Laplace transform cosine 2t. It's important to remember that when we go to Laplace transforms, all of our variables are always expressed in terms of t. And then once we take the Laplace transforms, then they become s. All the variables become s. Okay. This is 1/2, and the Laplace transform of 1, as we found, was just 1 over t. 1 over s, I mean. What was I just saying? So, the Laplace transform of something involving t becomes something involving s. And then plus 1/2, we want the Laplace transform of cosine, where 2 is going to be playing the role of the k. So k for cosine, but it's wrong, so you put in the s. And then down here, it's going to be s squared plus because it's trig. T for trig. So there we have it. And so this is going to be 1/2 s plus 1/2 s over s squared plus 4, which it will commonly be the case that such things as this will be re-expressed in terms of a common denominator. So this is going to be 1 over s times s squared plus 4 over s squared plus 4 plus s over s squared plus 4 times s over s. So what we have is 1, and I guess if I wanted to fully express this here, what would we have? We'd have 1/2, we'd have s squared plus 4 plus s squared divided by s times s squared plus 4, 1/2 2s squared plus 4 s squared plus 4, and the 2 can cancel. And so what we have is a grand result of s squared plus 2 over s times s squared plus 4. So once again, the magic of linearity has gotten us through. So this is the end of the functions that we had some pre-existing relationships with, but now let's make ourselves some new friends. So first off, let's go with some piecewise defined functions. So if we have a function that is defined in pieces, we can still find its Laplace transform, and that Laplace transform would just involve breaking the integral into corresponding pieces. So we can find the Laplace transforms of functions defined in pieces by breaking the integral into pieces. All right, so let's take as an example something called the unit step function, or the Heaviside function. Unit step function, also called the Heaviside function, named after an engineer. So first off, a picture of what it looks like. Or actually, I guess first off, just the definition. U of t is equal to the piecewise defined function that is 0 until it's not, and then it's 1. So it's constantly equal to 0 until it's constantly equal to 1. And the domains for each of these are that it's 0 as long as t is less than 0, and it equals 1 from then on, so t greater than or equal to 0. So then what the graph of this would look like is it is just going to equal 0, 0, 0, 0, 0, 0, 0, 0, 0. And then there's going to be a little jump. And it's just going to be constantly equal to 1. And we can vary this by starting it at a different point other than at 0 by default. So u sub a of t is the same as, so that's another way of writing u of t minus a, which is the same thing, except that whatever the value of a is now when the function basically turns on. So it's shifted right by a units. So let's say that we wanted to actually find the Laplace transform of these unit step functions, either the classic OG one, just u of t, or any of the shifted ones. Well, let's see what we can do. So the Laplace transform of the original one, that's going to be the integral from 0 to infinity of e to the negative st u of t dt. But if we think about this, if we think about what's going to be happening here, from 0 to infinity for a t, that's actually exactly when this function just equals 1. This actually just happens to equal 0 to infinity e to the negative st times 1 dt. And we've actually already seen this. This is the same as just the Laplace transform of the function constantly equal to 1, which is just going to equal 1 over s. What gives? Well, what gives is the Laplace transform only notices values of t from 0 to infinity. And so if the function equals 0 before that, the Laplace transform doesn't care. The Laplace transform is exclusively concerned with values of t that go from 0 to infinity. So the negative values need not apply. All right. Well, what if we shift it though? So that one was maybe a little too easy for us. We didn't get a chance to really challenge ourselves. So how about if we do u sub a of t? Well, if we think about that, that's going to be the integral 0 to infinity of e to the negative st u sub a, a of t dt. And now if I break the integral up to the stuff before a and the stuff after a, so 0 to a, just assuming here a is positive. If a is negative, then I'll let you use your imagination, think about what's going to happen. So 0 to a, e to the negative st times 0 dt. Interesting. And then the integral from a to infinity. And that's going to be e to the negative st times 1 dt. And what's that going to leave us here? 0. 0 for that one. And then for this one, it's going to be plus negative 1 over s e to the negative st, and we're putting in a and infinity, and by usual tokens of uh, token suggestions of what values of s we are allowed to be dealing with here, we can just note that e to the negative st is going to go to 0 as t goes to infinity if s is greater than 0. So we'll just presume that that is the case. And so what we're going to have is negative 1 over s, and that's going to be then a 0 minus e to the negative a s. So then what we have is finally something a little different, e to the as over s, which is going to turn out to be a pretty useful expression. We're going to actually see a lot more of this unit step function than you have any right to expect at this point, but it's happening. Okay, well let's summarize our findings so far and make ourselves a nice little table of Laplace transforms. All right, so we're gonna have f of t. We're gonna have capital F of s. And in all these cases, just assume that the s is defined in such a way that the integral converges. It's not that important. Not that important to worry about the conditions of definition for the s on these. Okay, so 1 becomes 1 over s, as we've seen. Just a t becomes 1 over s squared, as we've seen. T to the n. That is the same as n factorial over s to the n plus 1. This is where n is a positive integer. Or actually non-negative, I guess, technically. It's non-negative. Non-negative. Alright, what if it is not integral? Then, if we have t to the alpha, that's the same as gamma, alpha plus 1, over s to the power of alpha plus 1. How do you evaluate those gammas? By using the formulas that we saw. Alright, what else do we have? We have exponential function, e to the at is going to be 1 over s minus a. E to the at times f of t is going to equal, this one was capital F s minus a. Or I guess I wrote it with a c before, it doesn't matter. So this one is going to turn out to be useful in practice. Cosine kt. So s over s squared plus k squared, and it's t for trig. That's how you know it's plus, and it's s because it's cosine. Sine kt. So here, sine means k, and then on the bottom, t for trig, s squared plus k squared. The hyperbolic ones are the same, except that the plus becomes a minus downstairs. So cosh kt is going to be s over s squared minus k squared. Sinh kt is going to be k over s squared minus k squared. Alright, unit step function or heaviside function, u of t. It's going to become just 1 over s. Where have you seen that one before? At the very, very top of the table. Coincidence? Nope. And then u sub a of t, which is the same as u of t minus a. This is equal to e to the negative as over s. Again, strange looking one there, but very useful. Okay. Now, let's do some examples of finding ourselves some Laplace transforms of various things and then turning the tables and going the other way around. Okay, so let's take on a particularly messy example here, just so you can see what sometimes these things look like. So here's an example. Find the Laplace transform of t, or of f of t. For the function defined below. All right, so what we're going to have is a piecewise defined function, and it's going to be a mess, frankly. So we've got our first installment, which is a straight line going that way. Next installment is just going to be a flat line going this way. It's going to go from 2 out to 4. And then the third installment is going to be a steeper down. And that's going to be a 5. So here now, let's see how we can figure this out. Well, first off, we can just break this into 3 lines. Line 1, line 2, line 3. All right, well, f of t is equal to well, we need line 1. So let's think about this. So line 1, we can see that it is that it's a line of slope 1, y-intercept 0. So m equals 1, b equals 0. So that means we're just talking about y equals t. So this will just be t. And that's for 0 less than or equal to t less than or equal to 2. All right. Line 2 is pretty easy. The slope is equal to 0. And actually, we don't even need that. It's just a horizontal line at y equals 2. Okay, so that's not so bad. T and 2. Now the hard one is line 3. Line 3. So let's just say it contains the points 4, 2, and 5, 0. So that means the slope is going to be, well, you can see that just the rise over run. So the rise is going to be negative 2 over 1. So negative 1, or negative 2, I mean. And then, so by the way, this was 2 less than t less than or equal to 4. And so then if I plug in, if I just plug in a value, or the values for one of these points into y equals negative 2 times t plus b, I can solve for the b. Okay, so then what are we going to have? We can plug in 0 equals negative 2 times 5 plus b, so b equals negative 10. All right, so then we have our formula, y equals negative 2t minus 10. And that is for 4 less than t less than or equal to 5. Okay, so then our function, or sorry, our Laplace transform of our function here, we can break into 3 integrals, breaking down this into 3 little subintegrals. So 0 to 2 will be t, I'm just going to write it in this order, t e to the negative st dt. That'll be integral number 1. Integral number 2 will be the integral from 2 to 4. And this is going to be 2 times e to the negative st dt. And then plus finally integral number 3, which is going to be from 4 to 5 of negative 2t plus 10 e to the negative st dt. So I'll just call these I1, I2, and I3 and take them each separately. So integral number 1 is going to be the integral from 0 to 2 t e to the negative st dt. How do I do this? Well, we've already seen how to do this. It's just going to be a case of integration by parts. So u is going to equal t, dv is going to equal e to the negative st dt, du is dt, v then is negative 1 over s e to the negative st. And so then that takes us to I1 equals negative t over s e to the negative st 0 to 2 minus the integral from 0 to 2 negative 1 over s e to the negative st dt. Okay, so this was u times v. What made those? And minus the integral of v du. All right, what is this going to give us? So this is going to be negative 2 e to the negative 2s over s. And then if I plug in 0, it's going to be minus 0. Minus negative 0, I guess. So what do we have here? Plus 1 over s. And then if I take the integral of this, it's going to be another factor of s. And here, just one thing at a time here. So it's going to come out, it's going to be an extra factor of negative 1 over s. So this is negative 2e negative 2s over s minus 1 over s squared. And then this is going to be just e to the negative st. I plug in 2 e to the negative 2s. And then minus, I plug in 0, so it's just going to be 1. All right, so integral 1. I think we have got negative 2 e to the negative 2 s all over s minus 1 over s squared. Actually, e to the negative 2s on top of that s squared. And then what is it? Plus 1 over s squared. Okay, 1 down, 2 to go. So now we need integral number 2. Integral number 2. So this one is going to be a bit of a break from the harder integrals 1 and 3, because it's just the constant part. So 2 to 4 of just 2 e to the negative st dt. So that's just going to equal negative. So we can pull the 2 out. We can actually just go ahead and find the antiderivative. It's going to be negative 2 over s. And then what are we plugging in here? It's going to be 4. So it's going to be e to the negative 4 s. And then minus negative, minus e to the negative 2s. And so distribute it, and we're going to have negative 2 over negative 2 e to the negative 4s over s plus 2 e to the negative 2s over s. Okay, so that one was short. Didn't even need any fancy integration techniques, which is nice. And then integral number 3. Integral number 3, which is going to be the trickiest one because it involves the most pieces. Okay, so we are talking about the integral from 4 to 5 of negative 2t plus 10 e to the negative st dt, which we can break into the two pieces according to the terms of the integrand here, because the integral is linear. So 4, 5, negative 2t e to the negative st dt, plus the integral from 4 to 5 of 10 e to the negative st dt, which the second one here is the easier one out of the two because as we saw before, when we have just this constant, it's not going to be so bad. So let's focus our energies on the first one. And for the first one, we'll do integration by parts. I could pull the negative 2 out to the front, or I can just kind of accept it as written and not mess with it. So maybe I'll just do that. So u equals negative 2t then, meaning du would be negative 2 dt, which is interesting. And then as for the dv, that's going to be e to the negative st dt. V is going to equal negative 1 over s e to the negative st. And then if I want to break this up into its two pieces, I have to convert it into an integral involving u, which means I should figure out that dt is equal to negative 1/2 du. Okay, so then what's my integral going to be from t equals 4 to t equals 5? If I'm not planning on converting my integral completely into the pieces here. Oh wait, what am I doing? What am I doing? I don't have to worry about that. Scratch that. So for a second there, I got a little bit fatigued in all of our integrations, and I was about to do something that you have to do if you're doing a u substitution, but not something you have to do if it's an integration by parts. It is not our responsibility to make this fit our original integral. Our original integral is the integral of u dv. So it's up to the dv to match the original integral. Anyway, that said, so what we're doing here is now just going to be u times v, so it's negative 2t times negative 1 over s e to the negative st, plugging in 4 to 5, plus, what do we have for this next part? Or it's actually minus a negative minus the integral of v du. I'm going to be a hero. E to the negative st times negative 2 dt. Let's not go out on any limbs here. This is the integral from 4 to 5. And then plus the integral from 4 to 5 of the 10 e to the negative st dt. Okay. So now what have we got here? We plug in the t equals 5, the t equals 4, and that's going to give us negative and negative cancel each other. Let's go ahead and do that. So it's going to be 2 times 5 is going to be 10 over s e to the negative 5s minus, so it's going to be 4 times 2 is 8 e to the negative 4s all over s. What do we have now? Again, the plus, or the minus and the minus cancel each other, and we end up with a net that looks like a net of a minus. So we have minus, 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 so net minus. So it's going to be negative minus 2. Oh, but when we integrate this, actually we get an extra negative 1 over s, so it's going to be negative 2 times 1 over s, but it's going to become times another negative 1 over s, so it's going to be and so it's sort of like that. And then what do we have? E to the negative st from 4 to 5. Okay. So I think if I have all the right pieces in play there, I'll deal with the aftermath in a second. And then what's this going to be? It's going to be minus 1 over s times 10, and then e, just write e to the negative st, 4 to 5. I'm going to need another step anyway. Might as well not bite off more than I can chew. 10 e to the negative 5s over s minus 8 e to the negative 4s over s. Here, what do we have? Looks like those will cancel, and I'll have plus 2. We're going to have s squared on the bottom, and here it's going to be e to the negative 5s for the first one, minus 2e to the negative 4s over s squared for the second one. And then finally here, we're going to minus 10 e to the negative 5s over just an s, minus negative, so it's going to be plus 10 e to the negative 4s over just an s. All right. So everything looking good. We've got a little bit that can be combined. In fact, canceled. That cancels that. And these two can be combined. Good to know. So then if we combine them, what are we going to get? We're going to get 2e to the negative 4s over s plus 2e to the negative 5s over s squared minus 2e to the negative 4s over s squared. All right. Well then, we are ready to put the three pieces together. We have three integrals that we found separately. Oops, I1, I2, I3. So what do we got here? For our I1, we found that it equaled negative 2e to the negative 2s over s plus e to the negative 2s over s squared plus 1 over s squared. I2 was negative 2e to the negative 4s over s plus 2e to the negative 2s over s. And then on I3 we had plus 2e to the negative 4s over s plus 2e to the negative 5s over s squared minus 2e to the negative 4s over s squared. Okay, quick typo check. Anything go wrong there? I hope not. I hope not. Okay, well, where do I have like terms that can be combined? Starting with this one, we have, so it's negative 2s on top, and it's just an s on the bottom. That matches that. And in fact, those two cancel each other. Nice. All right, what else? Well, it looks like actually, while we're at it, these two are going to cancel each other as well. So that's nice. And then looking at the other four terms, I'm not seeing much scope for cancellation on those. So what are we going to have? I do see though that they all have a 1 over s squared as a factor shared by them all. So maybe I'll just put that. And what do I have? So e to the negative 2s. Wait, is that supposed to be negative or positive? So that one was supposed to be negative. So nope, negative there. If you saw that, good for you. I missed it. All right. So we have negative e to the negative 2s plus 1 plus 2e to the negative 5s minus 2e to the negative 4s. Okay, so there you go. The Laplace transform. So it can even be done when we have a piecewise defined function that might be a little bit awkward, but it can still be done by the same basic process of setting up the integral and evaluating. Now, setting up the integral sometimes the only way of going about something, but frequently there will be other options available. Let's take another example here. So this will be an example. F of t equals, let's just say t sine t. T sine t. So if I wanted, I could just set up the integral that defines the Laplace transform and use that to get this. However, if I do so, this is going to be complicated and it's going to involve integration by parts. So here's a quick note about this. So note. This not the real part, the imaginary part, I should say. Of e to the it times t. So the imaginary part of this would be, so this would be t cosine t plus I t sine t. So if we're talking about this, so if g of t equals t e to the it, that implies that the Laplace transform is going to equal, and this is, if we look back at our table, look back at the table here, this is actually something that we have covered. We have anything that is a factor of e to the at times a known character in the Laplace transform world. So this is going to just actually be this will be the Laplace transform of t with a little substitution here. So this is equal to e to the at times t. Oh, sorry, I should say g of t equals that with a equals I. So the Laplace transform is going to be the Laplace transform of t, which is 1 over s squared, but rather than it being s squared, it's going to be s minus I. So this is, so we use s minus I in place of s in the Laplace transform of just the t. So that's how this can go. And if we, and so then what we have is 1 over s minus I squared, and that is the same as 1 over s minus I times s minus I. I just multiply it out. And that, so that in turn is going to be 1 over s, and it's going to be squared. The cross terms will cancel, and we'll have negative I times negative I, which is 1 over s minus, oh sorry, the cross terms don't cancel here. This is not a perfect square. So it'll be minus 2is, and then plus I squared, so it's going to be minus 1. So that equals 1 over s squared minus 1 minus 2is, which we can multiply then by the conjugate, s squared minus 1 plus 2is, s squared minus 1 plus 2is, and so then downstairs what we're going to have is going to be s squared minus 1 squared plus 4s squared. Upstairs, what we're going to have is going to be just what we just wrote, s squared minus 1 plus 2is. And in reality, it's probably easiest to just leave it in this format to answer it. So then the imaginary part 2s over s squared minus 1 squared plus 4s squared. And there's not really, like I said, there's not really much profit in going around rewriting this extravagantly. If you wanted to, you could multiply out the bottom, combine the like terms, but there's not, like I said, not much going for you in doing that. So this would be how you could find the Laplace transform of something a little bit ungainly in that it doesn't quite fit into our table, but it almost does. Option number 2, by the way, would be just integrate this. So set up the integral that would define this and integrate by parts. The problem with that is you're going to have a more complicated integral than you have probably seen very often in your lives, because it'll have 3 functions in it. So you have to do a little bit trickier integration by parts, but it can be done if you are careful about it. Okay, well, now let's turn the tables around on this. I know it's a long section, but it's very important to get the lay of the land to begin with when it comes to these complicated topics. Let's turn the tables a little bit here and talk about the inverse. The inverse Laplace transform. So the goal here is to use our catalog to invert the process. So given f of s, we want to find f of t. This is called the inverse Laplace transform. And we write it with same script L and just a little inverse symbol. Okay. Let's just try this for a couple examples. And here, let's start with something straightforward. One that is easily put in terms of our table. So the Laplace transform inverse of 3 over s. Okay, so let's think about this. So this is the same as 3 times the inverse Laplace transform of just 1 over s. So the inverse Laplace transform is just as linear as the regular Laplace transform was. And if we look at our table, sure enough, that is exactly one of the charter members of our table. So this is actually just equal to 1. So this just equals 3. Okay. Well, that was nice. A little too nice, perhaps. Let's try something a little harder. So let's go with the inverse Laplace transform of s to the negative 3/2. All right. So let's think about that. So if f of s is s to the negative 3/2, that means, just try to reason it out, that's, for one thing, that's 1 over s to the 3/2, which means that that this is the form 1 over, or something over, s to the alpha plus 1. So I'm just going to write it as 1/2 plus 1. So just basically to make it fit the format. So alpha equals 1/2. Okay, well that's great, but that doesn't quite fit our pattern. Our pattern is supposed to have the gamma of alpha plus 1 on top. I mean, it's supposed to look like that, right? So essentially, what I do is I just do a little bit of wish fulfillment here, and I just multiply by multiply and divide by this in order to create something that keeps the same value but has the form that I want. So here I just I started with 1. So if I want to write it as a gamma, I have to also divide by that same gamma. Okay. So then, what do we have here? So this is seen to be the Laplace transform of t to the 1/2. So okay, so this is then f of t is equal to 1 over gamma 1/2 plus 1 times t to the 1/2. All right, quick thought here. What is gamma of 1/2 plus 1? Well, we already figured this out. Gamma 1/2 plus 1 is the gamma of 3/2, which is just equal to 1/2 square root of pi by the same logic as we figured out before. So this is equal to, okay, so then that means 1 over that. Is going to be the reciprocal of this, which will be a 2 on the top and root pi on the bottom. Two over root pi t to the 1/2. So that's how you can do something like that. Now, let's take a look at something else. So for some of these other cases, we are going to have to resort to some a little bit more sophisticated methods. In particular, don't be surprised to see your old friend partial fractions involved. So let's say we wanted to find the inverse Laplace transform of 1 over s times s minus 1. All right. Well, looking at this, we see two pieces that we actually feel pretty good about. 1 over s plus 1. We can work with either one of those. The problem is that that's not what we have. What we have is this. And we don't have any way of dealing with the Laplace transform of a product right now. It does turn out that there are things that can be done for situations like this, but that is unfortunately a little bit beyond our reach at the moment. But what we can do is partial fractions. So a, or actually I'll write it like this, 1 over s times s minus 1 is equal to some mystery a over s plus a mystery b over s minus 1. So what's that going to mean? That means 1 equals a times s minus 1 plus b times s. And here we have a nice little situation where we can just pick strategic values for for s. So s could equal 1, which would mean that that this would disappear and we get b equals 1. Or s could equal 0, in which case this one will disappear and we'll get a equals -1. And so 1 over s times s minus 1, that's the same as -1 over s plus 1 over s minus 1. And so the inverse Laplace transform of that will go along the same lines. So the inverse Laplace transform of -1 over s is just going to be -1. As for 1 over s minus 1, that is the same as 1 over s minus a, where a equals 1. This is going to be equal to e to the t. So, partial fractions. That's the key to this one. All right, let's take another example here. Let's go with something like the inverse Laplace transform of 3s over s squared plus 4. All right, so let's think about where things are here. So this looks an awful lot like the trig functions. And so in particular, if we remember the sine and the cosine, we want cosine kt because there's an s on the top, k for cosine. So this is equal to s over s squared plus k squared. Pretty close to what we've got over there. So what can we do? Well, k just has to equal 2, and then what we've just got here is we've got 3 times basically the exact thing we want. So I might as well just write cosine 2t. One step process on that one. Enjoy it while it lasts. All right. What about if we have something along the lines of something like this? So e. So if we have inverse Laplace transform of 1 over s minus 3 to the third power. S minus 3 to the third power. All right, so if this had just been 1 over s minus 3, we would have been great. So I should say Laplace transform of this, by the way. So the Laplace transform of just s minus 3 would be easy. Laplace transform, inverse Laplace of s minus 3 would be great. S to the third, I could work with that. So let's just start with the s to the third. Whenever you have something like this, if you see something that would be, if you see an expression that would be easy, if this were just s rather than s plus something or s minus something, go from there. So let's just say, let's just focus our sights on the inverse Laplace transform of 1 over s to the third. And if we think about this, this is going to be, this fits the format s to the n plus 1, where n is going to be 2. So we need a 2 factorial there. And then to balance it out, we need to divide by a 2 factorial. And so what's that going to equal? 1/2. And then the inverse Laplace 2 factorial s over 2 plus 1, which is exactly 1/2 t squared. Okay, so that is great. But that's not what we had here. But s is replaced by s minus 3. So what's that mean? That means that we multiply by e to the 3t. So then our answer here is f of t is equal to 1/2 t squared e to the 3t. So this is a tricky process, but once you get the hang of it, you'll see how it goes. Essentially, what happens is if we look at our table, we have this little property right here, where if you have s minus a instead of just an s, you take your original function that you would have produced and you multiply it by e to the at. So that's how that works. It's like I said, it's a tricky process, but once you get the hang of it, you'll get the hang of it. All right, now I'm just gonna give one last example of things going crazy here. So for our last exhibition, how about something like this? The inverse Laplace transform of 1 over s plus 3 squared times s squared minus 1. Okay. So once again, we are just going to try to take this apart, and we'll use partial fractions to do it. So 1 over s plus 3 squared, s squared minus 1. We want to decompose that into partial fractions. And here we have to remember that there's one kind of exceptional case that happens when you are doing partial fractions. You actually need to. Oh, sorry. This was squared, not cubed. Squared. You actually need to put in a second term that you don't ordinarily have to do to put in to account for the duplication here. So we have a over s plus 3 squared plus b over s plus 3. So remember, this is needed. Because of the squared factor. Now, technically here it would be possible, as we do this, to actually break this last part up into two terms, or the s plus 1 and s minus 1. However, it currently is actually pretty conveniently laid out for us as far as Laplace transforms go, because it already matches the hyperbolic trigonometric functions. So I think we would like to leave it the way it is. And if we do that, we have actually another little exception that we have to make. So here, if I wanted to have this, I can't just use C over this whole thing, because this has a higher degree than just 1. So I have to actually go CS plus D. And that's needed. Because of the squared term. So we actually have in here both of the kind of exceptional cases that have ever come up when dealing with partial fractions: multiplicity higher than one factor, and a degree higher than one down here. Usually, when you've seen it, it's probably been irreducible, but it works just the same way, even if it technically was factorable, but we just chose not to. Okay, so what's that going to take us to? It's going to take us to a equals, and if we multiply everything by a sufficient denominator to cancel the pieces here, we'll have a times s squared minus 1, b times s plus 3, one extra factor of that, times s squared minus 1, plus cs plus d times s plus 3 squared. Now, going around trying to choose strategic values of s to make the pieces all disappear is unfortunately not going to be super profitable for us here, because this has entered a new level of difficulty as far as the arrangement of it. So what we'll just do is multiply everything out and combine the like terms. So as squared minus a, what are we going to have here? We're going to b s to the third, so this is going to be minus b for just a constant, that'll be its own thing. Sorry, minus b times s, I should say. And then what are we going to have? We're going to have plus 3bs squared, and then finally minus 3b. Here, well, let's take it easy. So what are we going to have? Cs plus d times s squared plus 6s plus 9. And so minus a bs to the third minus bs plus 3b s squared minus 3b plus, okay, what are we going to have? We're going to have cs to the third plus 6cs plus 9, so cs squared, I should say, plus 9cs plus ds squared plus 6ds plus 9d. Photo finish there. Almost didn't make it on the page. Alright, we'll now collect all the pieces, and we'll have the s squared terms. Actually, what's the highest degree here? It looks like a third degree. So s to the third, so we have 0 on the left is equal to b plus c. Okay, well that's nice. May they all be that nice. Alright, how about s squared? So what do we have? We have 0 on the left and equals a plus 3b plus 6c plus d. Yeah. Alright. How about just s? So s. We've got 0 on the left equals negative b plus 9c plus 6d, and then constant. And for the constant terms, what have we got? We've got 1 on the left, we've got negative a, we've got minus 3b, so no c, because the only occurrence of c has an s attached to it for free, plus 9d. Alright, well, if you want to solve this, you can do it by some complicated sequence of substitutions, perhaps, but unless something jumps out at you right away, more likely you're just going to want to set this up as a matrix and just let somebody else do the hard work for you, namely a calculator. So how about you just set it up with a nice little augmented matrix where this will be for the A, for the B, for the C, for the D, and then this is the other side. Okay, so for the first one we have 0, 1, 1, 0, 0. For the second one we have 1, 3, 6, 1, and 0. We have 0, negative 1, 9, 6, 0, negative 1, negative 3, 0, 9, and 1. All right, I'm going to take a quick break to calculate this using some piece of technology. Also, check for typos. You never know what mistakes could have happened. All right, the jury is in. So I row reduced this using a calculator, a TI-89 specifically. And so this goes to 1, 0, 0, 0, 1/8. 0, 1, 0, 0, 3 over 32. 0, 0, 0, 0, 1, 0, negative 3 over 32. And then lastly, 0, 0, 0, 1, 5 over 32. Now, I put this in the calculator. I row reduced it using that. I got this answer. And then actually, I went back and checked that this answer made sense in the context of the original problem. The way I did that was I quickly put these numbers in for the A, B, C, and D, and I then just evaluated the expression at s equals 0, because that was easy to do in the original expression, and I got the same numbers. That gave me some validation that there hadn't even actually been a mistake up till there, which is something of a small miracle. But then what that means is that our function can then be rewritten in this partial fractions decomposition way as 1/8 times 1 over s plus 3 squared plus 3 32nds times 1 over just s plus 3. And then I'm going to write this in a slightly offbeat format. I'm going to go minus 3 over 32 times just the s over s squared minus 1. And again, I'm just trying to think about what would be more convenient, given that I'm planning on using a hyperbolic trigonometric function for this. And then for the last one, we've got 5 over 32, and that's just going to be over 1. So times 1 over s squared minus 1. Okay, well, here we actually have something very similar to what we saw just a second ago. This, if that were just s squared, that would go to 1 over t. And this is just like that, except that where I see an s, or where I should see an s, I see an s plus 3. So this fits into the format of those slight variations on the problems that we saw where you see something other than just a plain old s. Okay, so what's that going to mean then? That's going to mean we take what was going to be our answer, 1 over 8 times, s squared. What am I saying? What I meant was 1 over s squared would lead to just a t. So I take my 1/8 times my t, and instead of that, I have that times e to the ct or at, so e to the negative 3t for the first term. Plus what? Plus 3 over 32. This is going to be just e to the negative 3t. That one's nice and clean. This one is a nice clean 3 over 32 times cosh of t, and we can see that the k is just going to equal 1 here, as it is over here as well. You might, if k had not equaled 1, you might have had to adjust it so it would fit the format for sinh. But 5 over 32, now sinh t. Actually, on that note, let's finish this off with one more. I know I promised that was going to be the last one, but just in case you do end up with one of these with a k not equal to 1 for a sine or a sinh, how do you deal with it? So this will be nice and easy comparatively. Let's just do inverse Laplace transform of 1 over s squared minus 9. Okay, so this almost fits the pattern for sinh, but not quite. So how do we adjust it? You just take what you have, and you just rewrite it so that it fits the pattern exactly, and then see what changes you had to make. So to fit the pattern exactly, we need s squared minus 9, and this has to be k. So k is going to equal 3 here. So this will have to equal 3, and then to make that work, you just multiply by a 1 over 3 in the front. And so then what we would get is f of t here finally is just going to equal 1/3 sinh 3t. So that's how you make those adjustments on the if you happen to be in a situation where the k does not match your numerator. Okay. Well, that's enough of those. So now we're gonna call that a lesson and move on to some other things. So thank you for joining me for this episode of Math 256. I'll see you next time. Bye.